Okay, so storing energy without a battery requires something called a capacitor. And what a capacitor really is a sandwich made of two pieces of metal, usually aluminum foil, with some sort of insulator in between. This insulator is sometimes called a dielectric and is very commonly paper. So what do capacitors look like? Well, they range. So this is one where the sandwich has been rolled up. Okay, this is often called a can capacitor. So here's a slightly larger by size can capacitor. In our class in AP Physics 2, we're going to end up using these ones, which are very, very large indeed. So that's what a capacitor is. It's a little sandwich. And you store charge on one side, and you store charge on the other side, and the insulator in between prevents that charge from passing between the two. You can then disconnect power and the charge stays where it is, which is pretty cool. How much a capacitor can hold is called its capacitance. The capacity of something is just the capacity of a bucket is how much, say, water a bucket could hold. So the capacitance of a capacitor is the amount of charge per volt that it can store. And on your reference tables, the equation is listed like this. If capacitance is charge per volt, then it must have a unit of coulombs per volt. A coulomb per volt we decided to name after Michael Faraday, and so that is called 1 farad. The simplest type of capacitor, and the only kind we're really going to concern ourselves about here, is the parallel plate capacitor. If you look, this thing looks kind of like a sandwich. And so you can take it and roll it up, you can fold it into multiple layers, and the math is still very close to what you have for a parallel plate capacitor. And capacitance is a matter of materials and geometry. So here's the equation that shows the capacitance for a capacitor. You have kappa epsilon naught A over D. Epsilon naught you've seen before, right? A is the area, literally the physical size of one of the plates of the capacitor. D is the distance between the plates. The closer you can get them together without a spark jumping across, the more charge you can store per volt. Kappa is called the dielectric constant, and it's a measure of how good an insulator you have slid in between. The dielectric constant of a vacuum is 1. So the dielectric constant, if it's not specified in any kind of problem, you can just assume it's 1. But for rubber, it can be in the thousands and things like that. So this number can range a great deal, and if you need it, we'll give it to you. The electric field between the plates of a capacitor is also a matter of geometry and a matter of how much charge you've managed to pack on the plates. It's always an equal amount of charge on one plate to the other. Well, the electric field here is Q over epsilon naught A. Charge on top, area on the bottom. More charge, stronger field. Bigger area that charge is spread out over, weaker field. That should make good sense. So how much energy can a capacitor store? Well, check this out. Okay, so if we graph the voltage versus charge in a capacitor, we end up with a straight line. Now, the units of this line is 1 over capacitance, so this will be different for every capacitor with different capacitance. But now let's look at the area underneath this thing. So of course, what shape is this? This is a triangle, right? So area is equal to 1/2 base height, right? In this case, that's going to be 1/2. The base here is Q, and the height here is delta V, 1/2 Q delta V. And what is the units of that? Well, voltage is energy per charge, and so energy per charge times charge is energy. This is the potential energy stored in the capacitor, and it's 1/2 QV. Using the definition of charge in a capacitor, we say Q equals C delta V. We can substitute this in multiple times, and we can get several equations for energy, kind of like what we've done with electricity in the past. So like with Ohm's law, substituting in, stuff like that. So 1/2 QV is the same thing as 1/2 CV squared. You take this CV and you substitute it in up here for Q. And then you can substitute again, and you can get 1/2 Q squared over C as well. Those are all acceptable, but so your reference tables has the equation for energy on it, and then you can just substitute in as necessary. And so you may ask yourself, what if I don't have enough capacitance? Can I hook my capacitors together to get more? Well, it turns out that you can hook them together to get more, and you can also hook them together to get less. So it depends on how they're connected. So here are the rules for capacitors in parallel. When you hook capacitors together in parallel, what you've essentially done is merged them all into one piece of metal. If you look at this top section here, it's all connected to one side of the battery. And if you look at the bottom section, it's all connected to one side of the battery. So when this thing is in equilibrium, each of those capacitance halves have to be at the same voltage. So these capacitors all have the same potential difference across them. Charge is going to flow into each capacitor until the voltage across the capacitor cancels the voltage of the battery. So even though they all have the same voltage, they won't have the same charge unless they also have the same capacitance. Each one is going to store a charge Q equals C times V, and so the total charge is going to be the sum of the charges on each of the capacitors. And on your reference tables, that looks like this. Capacitors connected in parallel, add. And here are the rules for capacitors in series. By connecting these three capacitors in series, we've actually created 4 pieces of metal that aren't actually touching each other. And you can see each of them here. When positive charge builds up on plate 1, it attracts electrons from the second piece of metal containing plates 2 and 3. This second piece of metal polarizes, with electrons moving from plate 3 to plate 2, leaving behind protons, so 2 and 3 end up with the same charge. Repeat the process for 3 and 4, and so forth. The end result is that all of the capacitors carry the same charge. But as charge builds up on each of those plates, it's going to oppose the voltage from the battery, so each of the capacitors only sees part of the battery voltage. The voltage on all the capacitors add up to the voltage of the battery. With each capacitor only seeing some of the voltage, the total capacitance of the assembled circuit decreases as you add more capacitors in series. The equation looks like this, similar to the equation of resistors in parallel. And there you have it. That's the basics of capacitors. See you next time.